Welcome back. The objectives of this video to introduce functions, we'll identify the domain and range of functions, we'll evaluate some functions, and we'll explore increases and decreases in functions. A function is a mathematical relation that maps a set of input values to a set of output values such that each input value is mapped to exactly one output. The set of input values is called the domain, and the set of output values is called the range. We will also see the domain, or our inputs, are generally going to be our x's, and our range is going to be the y's. So a lot of our studies in functions will talk about inputs and outputs, x's and y's, domain and range. All the same kind of thing. We'll represent functions in 4 different ways. We'll look at them graphically, numerically, algebraically, and verbally. We'll start by evaluating a few functions. Given our function here, f of x, f is just the name of the function, x is the input of the function, so it tells us what our variable is 2x squared plus 5x. And we want to evaluate f of x plus f of 3. Well, f of x, that's just our function itself. And then f of 3, we can find out what the output is when we put 3 into our function. So f of 3 is equal to 2, and we put 3 in for x, 2 times 3 squared plus 5 times 3. Notice I protect my input with parentheses, and so 3 squared is 9, plus 15, and 18, and 15 is 33. Well, that's just f of 3, but now we want to add f of x to it, so our final answer then becomes 2x squared plus 5x plus 33. Finding f of 2x, that just means take 2x and replace everything in the function that's x with 2x. So f of 2x is equal to 2 times 2x squared, 2x is replacing x, plus 5 times 2x. So we protect our input with parentheses, and we get 2 times 4x squared plus 10x, and that is equivalent to 8x squared plus 10x. F of negative x, we're inputting the opposite of x in for everything that's x squared, so f of negative x is 2 times negative x, quantity squared, plus 5 times negative x. Well, negative x squared, we're squaring both the negative and the x, so that becomes, or stays, 2x squared, but then this becomes minus 5x. And finally, f of x plus 3. We replace every x with x plus 3. So f of x plus 3 is equivalent to 2 times x plus 3 quantity squared plus 5 times x plus 3. PEMDAS tells us to do exponents before we multiply, so we're going to multiply out x plus 3 quantity squared. You should know that multiplication pattern. So that's x squared plus 6x plus 9 plus, and this will make that 5x plus 15 right away. We'll distribute that 5. We'll go ahead and distribute our 2 now. We get 2x squared plus 12x plus 18 plus 5x plus 15. We'll combine all of our like terms, and our final answer is equal to 2x squared plus 17x plus 33. So we've got some more notes up here about a function and finding the domain. If a function is defined by an equation and no domain is specified, then the domain will be the largest set of real numbers for which the value of f of x, y, that's our output, is a real number. Exclude any real numbers from a function's domain that cause division by 0. So you cannot divide by 0. So 0 in the denominator makes our fraction undefined. So if we have some number over 0, our fraction becomes undefined, or that result in a even root of a negative number. So if we're taking the square root or the fourth root and we get a negative number under that root, that's going to result in an imaginary result. So an even root, so any even index, not just 2 and 4. Find the domain and range in each of the relations below. And we'll determine if the relation is a function. So we have a bunch of ordered pairs here. We have some x's and y's. So our domain is going to be the set of x's. So in this case, 7, -3, 1, 3, and 2. Those are only x values in this relation. Our range then, our y values, are -2, 5, 6, -4, and 5. Now, is this a function? Well, it is, even though our range has a duplicate value of 5. Well, if we input 2, we output 5, and if we input -3, we output 5. That's okay. We know exactly what we're getting based on our inputs. That's okay. There's 2 different ways to produce 5 in our function, and that is a legal, if you will, way to define a function. B, on the other hand, this one is just a relation. We see here this 2 is mapping or leading to both 0 and -2. So if we input 2, we don't know what we're going to get. We might get 0, we might get -2. Whereas in sample A here, when we input -3, we were going to get 5. So we knew if we input -3, we'll get 5. And we knew if we input 2, we're going to get 5. All good. A lot of times you'll hear me talk about functions in terms of Willy Wonka and the Chocolate Factory. Willy Wonka makes both Wonka bars and gobstoppers. He puts his ingredients in, and he gets gobstoppers, puts a different set of ingredients in, he gets Wonka bars. Well, you don't want to be, if you're running a chocolate factory, you don't want to be putting in some set of ingredients where you might get Wonka bars and you might get gobstoppers. Both are good results, but not any way to run your business. We definitely want to know what our output is based on our input. And here in B, when we input 2, we're not sure what we're going to get. So this is going to be a relation. The domain here, our x's, I'm just going to make this real easy. Our domain is our x's, our range is our y's. We could put that in set notation like I did in the previous problem. Problem C, we've got a graphic representation, the arrowhead meaning this is going to head off to infinity. That just keeps on going. The closed dot here meaning we've started, or we're going to include that x value of -4, and we're going to include that y value of -2. So our domain, or our x's, they go from -4 and they're going to go all the way out to infinity. Our domain goes from -4 out to infinity. We do interval notation, so inclusive is the bracket and non-inclusive is the parentheses. Our range is our y values. We don't have any y's below -2, but this thing is going to keep on going, and this is going to go up to infinity. So for our y values, or our range, our minimum y value is -2, and that also will go to infinity, and this is indeed a function. Problem D, this graph, this is a function as well. For every x, we have a definite y. There's no ambiguity here. But we've got some things going on here with these dashed lines indicate asymptotes. These are x values here at 4, that's kind of blocked off. That's our function can't use an x value of 4. So when I look at my domain, I see that x can't be 4, and I've got this hole here. This is called a point of discontinuity here in this graph, or a hole. It looks like when I input an x of 2, this thing jumps over that x value of 2. So x can't be 4 and x can't be 2, but it can be anything else. So it looks like our domain here stretches from negative infinity to 2, and then that's going to be in union with 2 all the way to 4, but not quite 4, right? We can't include 4, in union with 4 out to infinity. So the u here meaning union. In the range of this function, the y values, it looks like we can have any y value, well, except -2. We can't have a y of -2. And it looks like we can't have a y value of 5. So in our range, y can't equal, what did I say, -2, and y can't equal 5. But it can be everything else. Let's take a look at our range. Our range is going to go from negative infinity to -2, and that's going to be in union with -2 then to 5, in union with 5 to positive infinity. So we use parentheses to show non-inclusive, and there's our domain and our range, and this too is a function. Problems E and F, we don't have graphs, we have functions. We have a quadratic here. Some of you guys might know that the quadratic, a graph of that, is a parabola, and in F we have a square root function, and square root functions are going to look something like that. So let's take a look. We might have to do a table of values to see what this looks like. An easy one we can do is the x-intercepts, or pardon me, the y-intercept. We can see the y-intercept is 0. When we put 0 for x, we get y is 0. So we might want to do that. Let's just do a quick table here. X and y, when x is 0, y is 0. We might want to check 1. When x is 1, we get 1 plus 3. So when x is 1, y is 4. When x is -1, y is, what do we get? 1 minus 3, so -2. Check -2, which would be 4 minus 6, and we get -2 again. So we've got a graph that looks something like this. It's a parabola, so it's going to be symmetrical. So we'll have a point here, and we'll have a point here. So this is going to look something like that. Our axis of symmetry then here, since we see that these are symmetrical, is going to fall right between -2 and -1. So our axis of symmetry is at -3/2. And when we input -3/2, we get a y of -9/4. So just down here at -2 1/4. So here's our parabola. We don't have any y values that are below -9/4, but everything above, we can put anything in for x that we want. So our domain is going to go from -infinity to positive infinity, and our range will then extend the lowest value at -9/4, and our y values extend all the way to infinity. Our square root function, again, we can do a table of values here, find out, like, we could probably eyeball when the number under the square root is going to be 0. So if I do an x value of 2, I'm going to get a y value of 0. And really, I can't do an x value of greater than 2. If we look at this, 4 minus 2x has got to be greater than 0, which means negative 2x has got to be greater than or equal to negative 4. So x has got to be less than 2. So this is the maximum x value that we can have in our domain. So our domain, we can already see, our domain is going to extend from negative infinity all the way to 2. That negative infinity should have a parenthesis to it. Our range, when we look at our range, well, we can't take the square root of a number and get anything that is less than 0. So our range will extend from 0 all the way to infinity.
That 0 should be
and
inclusive.
our graph will look something like that. And I know that when x is 0, y is 2. So I went through that particular point there. So our graph is going to look something like that. And we've got our domain and range. Both of these guys are functions. Because of the way they are mapped, right? Every x has its own y, and we don't have an x that goes to two different y values. So this wraps up our video on defining functions and evaluating functions and introducing the domain and range of functions. And we'll explore the increases and decreases of functions in a different video. And with that, I will see you in class.